So dear students, different cases involving change in entropy. Now, to understand the concepts that we have learned so far, it's always good that we do enough number of numerical problems. As you know, doing these problems will give clarity to the concepts that we have already learned, and also it will help us to understand where to apply the different equations that we have already learned. So we will do some different kinds of problems, and you can do additional problems by your own. And I will first discuss the common cases or different types of numerical problems that you may come across, where you can use the equations we have already discussed. I'm dividing the problems involving change in entropy into some 3 or 4 categories. So the first type of problems maybe including some reservoirs and the heat transfer. Problems involving reservoirs and the heat transfer between them. So this is one very common kind of numerical problem involving the entropy change. So in this case, you can always apply the defining equation of entropy, which is if it is a finite change, then I can use delta S, the change in entropy of the reservoir. Any of the reservoirs, the change in entropy can be calculated separately. So delta S for the reservoir can be calculated directly as the total heat that is transferred upon the temperature at which the heat transfer has occurred. So if it's a hot reservoir, so then the heat transferred from the hot reservoir divided by the temperature of the hot reservoir you have to take. So this equation in general has been taken from the general equation for entropy change for infinitesimal process. ds is equal to dqr by t, and suppose that we have performed the integration so that instead of ds you'll be getting a finite entropy change delta S, and dqr is replaced by, you can say, like q. Okay, that is the thing. And in this case, since we are dealing with the reservoirs, temperature reservoirs, since the reservoirs are having infinite heat capacities, during heat transfer the temperature of the reservoir remains practically constant. That is why we are treating the temperature as a constant during the process. Okay, so this is the equation. Delta S is equal to simply Q by T, and Q will be taken as positive. Okay, Q is positive if heat gain occurs for a reservoir. Q is positive for heat gain, means usually the low temperature reservoir will be gaining, okay, heat gain, and Q is negative for heat loss. So that is the thing. So delta S for one reservoir will be positive and delta S for the other reservoir will be negative. So if you want to find out the total change in entropy, you have to add the delta S for the individual reservoirs which we have calculated. That will give you the total change in entropy for the collective system combining the two reservoirs. That is one kind of problem that you can deal. Now the second kind of problem that is very common is problems involving some processes undergone by ideal gas systems. And we have discussed, or we have derived different equations connected with the entropy change of ideal gas systems, and finally we arrived at some special cases for certain processes like isothermal, isobaric and isochoric. Let me recollect here those equations for isothermal. So delta S for isothermal case, I'm writing T here. T denotes that temperature remains constant. So this is for isothermal process for an ideal gas, n moles of an ideal gas. This equation we have obtained is nR log V2 by V1. You can just check it back. And for an isothermal process, PV equal to constant, or P is inversely proportional to V. So when you do that one in terms of pressure, it will be minus nR log in terms of pressure, minus nR log P2 by P1. That is one equation. And another expression, so this one was for isothermal process. In the case of isobaric process, so I am writing delta S with the P constant. This is P denotes here isobaric. So that is equal to Cp. It will be then in terms of Cp, heat capacity at a constant pressure, Cp log T2 by T1, either this is the equation, or it will be equal to Cp log. Okay, what will be the thing here? Already pressure has been considered, so the variables here are temperature and volume, so it will be V2 by V1. The reason is that for isobaric process, volume is directly proportional to the temperature. So T2 by T1 is equal to V2 by V1. Both are positive equations. That is the reason. Now the third case is the entropy change during isochoric process. So V. Okay. So when it is isochoric, instead of Cp it will be Cv. It's quite easy. Instead of Cp it will be Cv. Then Cv log, other things will remain the same, T2 by T1, and that is easy if you just make a comparison and learn the equations. Or it is also Cv log. So already we have taken volume constant, and so the variables are temperature and pressure. So it will be Cv log P2 by P1. So just have a close look at the symmetry of the equation, which will help you to easily recall. So you can see that wherever there is a pressure involved, there will be Cp here. Where there is a volume involved, there will be a Cv here. And when it is temperature, it will be nR here. All other things are very similar. Okay, so this is one problem that we can usually come across. The third type of kind of problem or category of problem will be involving some heating or cooling of certain sample of a substance. Okay, for example, water or some liquid is heated from some temperature T1 to T2, and you are asked to find out what is the entropy change that is happening. So problems involving temperature change. Problems involving temperature change means heating or cooling problems. So in these problems, okay, heating cooling problems, what we can do is that we can use delta S is equal to, again, delta S, or generally we have got ds is equal to dq by t. I'm not using d bar q at all, dq by t, because we are doing numericals, that's all. Okay, and always remember we are considering the process to be reversible. All these processes are assumed to be reversible. Okay, and also we assume that the process all these integrations can be performed directly. Okay, so ds equal to dq by t. So therefore in temperature changing problems we'll be using delta S. This is for the finite change, so you have to do the integration from some initial temperature T1 to final temperature T2 for ds. ds is equal to dq upon t. Now what we have to do, we have to just make substitutions. Okay, in the during heating or cooling process, what is important is the specific heat capacity. So we have the relation that the heat capacity, heat capacity capital C, that is equal to dq by dt, is not dq by dt in general. Heat capacity at is not, okay, so C is equal to dq by dt. Therefore you can write dq is equal to, we have done we have used this equation in problems when we discussed mixing of liquids, all those problems in the previous module. So dq is equal to simply C into dt. dq is equal to capital C into dt. And in capital C is the heat capacity. But usually what will be given is specific capacity, small c. So what will be small c is equal to? Small c is equal to capital C divided by m. C by m. Right? Okay, for solids we are defining this small c equal to capital C. For in general, small c equal to capital C by m. So wherever you see capital C, you can write as m into small c. So that is where you get the equation dq is equal to mc dt. Hope you remember this equation when I write this one. We have done problems using this one with the law of mixtures. Okay, mixing one liquid with another liquid and all, finding the resulting temperature. We have practiced some problems in the previous module, and at that time I told you that I need all these concepts later when we do problems in what you call the entropy. And here is what I am just using it again. So wherever you find dq, you will be able to write this one as mc dt. So what I can do is that I can just substitute dq as what? mc dt. So what will this equation becoming? That is t1 to t2, t1 to t2, dq is mc dt. So mc dt upon t. Now if you just regard, or if you consider that heat capacity for the given range of temperatures T1 to T2, if you consider that if you neglect the variation in the heat capacity for the range of temperatures used, then you can take M and C both go outside. So it will be equal to simply MC, okay, from T1 to T2, it reduces MC T1 to T2 dt upon T, or 1 by dt, okay, and you know what will be the answer. So it will be equal to simply MC, okay, MC log T2, T2 is T final divided by T1, and this will be one equation that would be handy for us in all these problems. Is it okay? Now fourth category of problems will be involving some sort of phase transition, especially we will be dealing with the first order phase transitions. Okay, so problems involving phase transitions. There are phase transitions, a very broad category of phenomena, but we are limiting ourselves to first order phase transitions involving, you know, what is first order phase transition? They involves what is known as latent heat. Phase transitions involving latent heat means just conversion of ice to water, then maybe from water to liquid water to steam, etc. Okay, and you know this phase transition, this first order phase transitions, they all occur at some constant temperature. So they are isothermal processes, and we consider them to be reversible. You know, okay, water can nearly they are reversible. Steam can condense to water, and water can boil to become steam. So it's considered to be almost reversible process. Okay, so isothermal reversible process. So phase transition involving latent heat. So this is the fourth category of problems that we have to usually deal with, latent heat. So in this case, what I have to do, it's the same equation that I have to make use of. This delta S I have to calculate. So in this case, what I have to do is that delta S is equal to, you'll be using delta S is equal to this Q divided by T itself. Q divided by T itself. So the same equation that we are fundamentally using, delta is equal to Q by T itself, but Q can be written as M into L, so by T. Why this M into L? Where L is the latent heat. Okay, because we have defined the latent heat during phase transition is equal to the heat required per unit mass of the sample. Okay, so therefore from this you will get Q can be written in terms of latent heat is equal to product of mass into the latent heat, and this expression we are substituting in this equation. So Q equal to M into L by T. So depending on whether it is solid, liquid, or liquid to gas, you have to use the latent heat of fusion or latent heat of vaporization. Usually those data will be provided along with the problem. So the problem itself is, or the data given along with the problem itself will give you a hint regarding what way you have to proceed in solving the problem. So this is usually another, what do you say, okay, kind of, or another group of problems that you can get. Now, if needed, there is there. If you want, you can just say that there is yet another type of problem that is very common. That is mixing of liquids. Problems involving mixing of okay, liquids, mixing of liquids at two different temperatures. It can be similar liquids or different liquids. Okay, say T1 and T2. And this is where we have discussed the law of mixtures in earlier module. And so in this case, how to calculate the total change in entropy? What you have to do is that first of all, you will have to find out the resulting temperature. What will be the resulting temperature of the mixture? Then you have to individually calculate the change in entropy for each liquid. Okay, suppose that is a liquid at low temperature mixed with a liquid with a high temperature. So there will be an intermediate temperature. So for the first liquid, you have to calculate what will be the entropy change from going from low temperature to the intermediate temperature. So there will be a rise in entropy for that liquid. For the other liquid, what will happen? That the temperature decreases. So you have to calculate from high temperature to the intermediate temperature. So there will be delta S1 and delta S2. You add the two, you will be getting the total change in entropy of the system or the mixture, right? And in general, you always remember delta S for the universe is equal to delta S for the particular system plus delta S for the surrounding. So if you are asked to find out delta S of the universe, see, always you calculate the delta S for the system and the delta S for the surrounding. You add up. Surrounding will be mostly the reservoir. Okay, so you just add them, you will get one delta S of the universe. So these are the common problems and its strategy, and we will do one by one, problems one by one. I will try to include examples for problems from each of these different category, so that you will be able to practice other problems by yourself. So let's see the problems in the next sessions. Thank you.